Okay, let's get started. So, when is your P-Set 7 due? Friday, and then when is your last P-Set due? On the final day at midnight or when? Before class, okay? So I put that in the P-Set just to be absolutely sure, but it's due before the final because no one's going to want to work on that after the final anyway. Let's see, what else did I want to say? I guess I don't really have anything. Are there any questions before we start? Yeah.
We're going to spend more time working on like reductions to NP problems today, or is that something we should understand already?
We're going to do one more reduction to something called a Hamiltonian path problem that I mentioned at the end of last time. Then we're going to talk about p-space completeness, which is basically a space analog of polynomial time. And then we'll do one reduction there to show that a p-space complete problem. I doubt we'll get to that today, but we'll probably get to that on Friday. And then I'll talk a little more about different kinds of reductions and other complexity classes, other techniques on Friday, just as a grab bag lecture. And then that'll be it. But are there other questions? Okay, so we've been talking about these two classes, P and NP. So what does the P stand for? Polynomial. And then what does NP stand for? Not polynomial? Non-deterministic polynomial. Good. So what were we able to show last time? Yeah, we showed, more importantly, that there is an NP-complete problem, but namely that 3-set is NP-complete. And then how did we do that? We looked at an arbitrary language in NP because we didn't have a NP-complete language to work with. And then we said, well, maybe let's model the computation of that machine as a formula, such that the formula is true if and only if the machine accepts a particular input. And then because of that equivalence and that it runs in polynomial time, the conversion I mean, therefore 3-set must be NP-complete. But what else did we show was NP-complete? The clique or the click problem, yeah. And what was this problem about? It's not a hypothetical. What was the clique problem about? Oh yeah, so we're looking at a graph now, and we're given an integer k as well, and we wanted to know, does the graph contain a subgraph of size k that has every possible edge between those k vertices? So I kind of wanted to address that a little bit. Suppose that I could do this. So I get this graph g and this integer k, and what I do is look at all n choose k subsets of size k, I mean the vertices, and check whether or not all k choose 2 edges present in that subset. Well, you can actually show that this, the first part is at most n to the k, and then the second one is at most k squared. So this is an n to the k times k squared algorithm. But doesn't that show its polynomial time? P equals NP. So let's see, this is, don't quote me when I said that, time algorithm, right? Because I just look at every k subset, and for each one, I just look at all possible edges. If all of them are there, great. If not, then I check the next subset. So I'm not taking into consideration the graph structure or anything like that, just brute force everything. But it looks polynomial to me. It's n to the k times another polynomial, so therefore it's a polynomial time algorithm.
It's not fixed.
K is not fixed, right? So remember, for a polynomial time algorithm, if k is given as part of the input, if it's upstairs here, then it's not a polynomial time algorithm. Namely, just as an exercise, if k is roughly n over 2, then this thing behaves something like n to the n subsets. But that is definitely not a polynomial. But if I instead said the graph contains a k-clique and I don't provide k as an input, then and k is a fixed number, is this a polynomial time algorithm? Yeah, because k is fixed now. It's not part of the input that I give to you. The original problem says I can feed you 2, 3, 4, 100, whatever. I can feed you any number I want, but if I fix it to say 5 and I never change it, then it must be a polynomial time algorithm. Okay, does that make sense? So the difference between what is provided as part of the input and when it isn't, the difference between whether it is polynomial time versus when it's NP complete, and probably not a polynomial time algorithm. Any questions on that? Okay, so what was the problem that I mentioned that we'll show is NP complete last time? Not Hamiltonian cycle, but Hamiltonian path, yeah. So we looked at this problem, or we just started talking about it. G is a graph, but G has a Hamiltonian path. Hamiltonian cycle is almost exactly the same as this, but there's some work to do there. But we're going to focus right now on the directed case. So we're going to only focus on directed graphs for now, and then we'll go back to undirected graphs because there's a little bit of work to do there as well. So wait, what was this Hamiltonian path thing? Just what is a Hamiltonian path? Right, so it's a path that goes through every vertex exactly once. So I can't. Here's an example of a graph. Does this have a Hamiltonian path? Yeah, so I can start at any of the 4 endpoints, and I can go to the other one on the same side, through the middle, then to one of the other 2, and then down. If I start at the middle vertex, is there a Hamiltonian path where I fix the first vertex to be that one? No, because I have to go through the middle to get to the other 2 vertices. So if I leave any vertex out, then it's not a Hamiltonian path. Okay? Which is actually going to be kind of important in the reduction. But any questions on what a Hamiltonian path is or the problem that we're considering? So the only thing that we're given is a graph, a directed graph in this case. And we want to know whether it has a Hamiltonian path or not. So what did we show about HAMPATH last time? We want to show as NP complete. What 2 things do I need to show as NP complete? That is in NP and NP hard. Which one did we do last time? Well, we didn't do NP hard. We just showed it was an NP. Why is it an NP? Oh, how about like the certificate just be the path itself? Just check if every vertex is there and none are repeated, and every edge along the way actually is an edge in the graph. So we're not like cutting corners or something like that. So, and that's easy to check in polynomial time. So therefore, this problem is an NP. Okay, but we would want to show that this is NP hard. And so what we're going to show pretty much the entire first half of the class is, because it's a long reduction in some sense, HAMPATH is NP hard. So I'm just going to say straight up for this reduction, it is very difficult in terms of being able to figure this out. So maybe for like the clique one, when we did 3-set to clique, maybe you could spend an afternoon or a few days thinking about how you would actually do that. And it seems conceivable that you can do it. For this one, I don't see how anyone in a short amount of time can conceive of doing this. So the proof is straightforward, but it just seems like something that someone just pulled out of pulled a rabbit out of a hat or something. So I just don't want you to be discouraged about it. Okay. So first off, if we want to show it's NP hard, what do we do? Do a reduction from. Could we do a reduction from any language in NP to this problem? In principle, could we do that? Yeah, in a style similar to the 3-set proof that we did. So, and actually, that's something I wanted to mention. I forgot to name the name of the proof of 3-set being an NP complete. This is called the Cook-Levin Theorem. My apologies for not mentioning the name of that.
Curiosity, how long did they work on that to come up with that?
So I don't know the whole history of it, but I know that Stephen Cook was working at I think Berkeley, but some American university, and he published this proof in 1971. And Levin, who was working in the USSR at the time because it was still the USSR, the proof didn't come to the United States until a few years later. So as to who came up with it first, we're basically just saying that they both came up with the idea simultaneously, although with completely different methods here. So in fact, in neither paper is the word NP or NP completeness actually mentioned. So what they thought of instead is having problems being polynomially equivalent to each other. So like in terms of how long it takes to solve a particular problem, up to a polynomial difference in runtime, they're the same problem. So that's actually the same notion that we have for NP complete, because we have these polynomial time reductions between the problems. So that was the basic overview, but I know there's a lot more to this. And some people actually put a third author along with this theorem. I don't know the name of him, though. Other questions? So if I mention Cook-Levin Theorem on the final, for example, no hint there, by the way, what problem am I referring to? Good. All right. Unfortunately, none of the other NP-complete problems have a nice name like that. But in fact, I don't even know who came up with the reductions in the first place. I know there's a book full of these reductions, but I don't know in terms of like who originally came up with these. But anyway, let's go on to the HAMPATH NP hard proof. So we got to reduce. We don't want to reduce from every single NP problem because that is basically doing the work of the 3-set reduction all over again. So instead, what should we reduce from? Well, we can do 3-set, or in general, what should we try to reduce from? Some NP-complete problem, right? If we do any NP-complete problem and we show the reduction works in polynomial time, then we're okay. I could do this from clique. So there is a way to do this from clique, but the more straightforward, even though it'll take a long time to get all the details, is from 3-set. So we'll actually show that 3-set is polyreducible to HAMPATH. And that will show that it's NP hard because any problem can reduce to 3-set in polytime. And then by this, 3-set reduces to HAMPATH. So a composition of polytime reductions is also a polytime reduction. And then we're okay. Okay, so what is the general idea? Well, we want to transform a formula, or a 3-set formula, and we want to produce a graph. Right? So that's the general thing that we want to actually do. And we want it to be such that the formula is true if and only if the resulting graph that we make has a Hamiltonian path. Right? We can't just produce any old graph based off the input. It needs to be based on whether the original formula was satisfiable or not. Okay, so let's look at what a formula may look like. So it's 3-set, so it's going to look like some clause at the beginning. And let's say A2, B2, C2, and then all the way to, let's say, K of them. Oops. BK, CK. So that's what a formula in 3CNF might look like. Well, the way that NP completeness reductions are done back then as well as still today in research is if we're going to reduce from 3-set, then we're going to have what are called gadgets. So in this case, since we have variables and clauses, what we would want to have in the resulting graph is a little mini graph to represent a variable, and then we'll connect up these variable gadgets together with what are called clause gadgets. So we're going to make a whole bunch of variable gadgets, one for each of these, and then we're just going to connect them up to some clause gadget in some way, and then we'll try to argue whether or not there is a Hamiltonian path or not. Question for you. So if we want to make a variable gadget, so think about what a variable could be. What values can a variable take on? True or false? So in some sense, what we want the resulting variable gadget to be is to have 2 of something, okay? So for example, since this is a directed graph, maybe one would want to have 2 directed paths through this little variable gadget graph. One to represent that the variable is true, and the other one to represent that the variable is false. And we can guarantee this because it's a directed graph. If it's undirected, then we can't guarantee anything. But if it's directed, then we have no issue here. So let's make a variable gadget. And there are many ways we can make a variable gadget here. This is not the only way that you can do it, but this is the more straightforward way. Remember, we still have to connect the variable gadget up to whatever clause gadget we think of. So the way we're going to do this is, let's say we're talking about the A1 variable. Then we're going to have a vertex at the top, and then 2 directed paths down to 2 vertices. And this is not really enough because if I want to take one of the paths down, if I want a Hamiltonian path at the end, I still have to visit the other vertex somehow. So what we're going to do is I'm going to have a whole bunch of vertices in the middle. And I'm going to have a whole bunch of directed edges in the middle going one way, and back edges as well going the other way. So I haven't said how many vertices that are going to be in the middle, but we'll get there. So I'm just going to say that there are a lot of vertices in there, sufficiently many vertices. to accomplish what we're going to do in a bit. And then what we're going to do at the very end is the two end vertices are going to have two more directed paths coming down to a central vertex below them. So I'm going to have a vertex down here, path there, path there. Okay? So this is a variable gadget. And I'm going to make one of these for every variable in the formula. Question for you. How many directed paths are there from the top vertex down to the bottom vertex? Paths, they cannot repeat a vertex. So at the beginning, I have to pick one of the two sides to go to, right? But there are four, right? So so four. So I can either just ignore the middle vertices, right, and just go down the two edges on either side, or I can just take one of the edges to this one side, go across, and I can't go back because then I'll be repeating a vertex. So I have to go all the way through to the other side and then back down, or I can take the other side and then go across and then down. So there are four directed paths here. How many Hamiltonian paths are there? Two. So that's where we are going to get the two either true or false idea from. So we got to think, well, since there are two Hamiltonian paths, it might be a good idea to assign one of them to represent true and the other one to represent this variable is false. Okay? So what we're going to, so I can do this the other way, but just as a convention, if we're going to the right, we're going to represent that as true. This variable is true, and then the other direction as being false. Okay? Any issue with that? I could say that going left is true and going right is false, but the connection with the clause gadget at the end is going to be slightly different, but it's not going to impact it too much. But any questions about that? Okay, then I'm going to make one of these variable gadgets for every variable in the formula. Then I'm going to vertically connect them up. So you see that there's one vertex at the bottom here. I'm going to connect it to the top of another variable gadget. So we're going to have another variable gadget. So I'm not going to draw the whole thing. But so something like this. So this will be, actually let's call the first one x1, meaning some variable x1, and then x2 will be the second variable gadget, and then if we keep doing this, so this is going to have paths out again, and if we keep doing this, then we're going to have the very last gadget. Okay, so again, each of these gadgets is going to be identical. So it's going to have all these middle vertices in each of the variable gadgets, and we're going to make one variable gadget for every single variable. Okay? Question for you. How many Hamiltonian paths, if there are n variables, are there from the top vertex all the way to the very bottom vertex? Well, I have two choices for the first one. Whichever one I pick, does it matter what I pick the first one for the second one? No. So, and in fact, how many Hamiltonian paths are there to the n? For a formula with n variables, how many ways are there I could assign truth values to the n? Do you think that's a coincidence? No. And in fact, we're doing all to the n possibilities right here. But of course, if I just produced this graph, I didn't take into account anything about the clauses. So in fact, there is a Hamiltonian path in this graph, mainly many of them, right? Because I could just pick any one of the 2 to the n of them, and all of them are Hamiltonian paths so far. So now we got to incorporate the clause, or what things are clauses. So how are we going to do that? So here's what we're going to do. So let's try to blow up the one of the rows, so one of the long chains of vertices. So let's say that, so we're going to make this a lot bigger. Okay, so let's see. Well, what did we represent by going to the right? We represented that being true in our construction idea, and going the other way represents the variable being false. Another way we can think of this as the going right represents the variable in this clause, meaning that it's in the positive form. So let's say that this is variable xi, for example. And let's say that the clause is xi or xj or xk. So in this clause, is xi in the positive or the negative form? It's in the positive one, right? If I put a bar over it, it would be in the negative form. So here's what we're going to do. I'm going to isolate 2 vertices in here. Say these 2. It will be important which 2 I pick, but I'm just showing you. I'm going to pick 2 adjacent vertices here. And what we're going to do is we're going to assign. Let's say that this is clause M. So some clause M. The clause gadget by itself is just a single vertex. And I'm going to label it CM. So it's in the positive form here. So in some sense, if xi is true, then CM is true or false. It should be true, because if xi is true, then the whole clause is true. Meaning, I should probably visit the clause gadget if I'm going that way in the direction. So if I'm going the positive direction in the variable gadget, then I should be able to go to that clause gadget and back. And then keep on going, right? Because I can't go back, because then I'll be repeating vertices. So what we're going to do here is, on the left vertex, it's going to go up to the clause gadget as a directed edge, and then it's going to come back on a directed edge to the next vertex. Okay? Question. If I'm going the negative direction, the other way, I could visit CM, right? So if I go to the right vertex, go across, and then I take the left vertex up to CM, could I come back to this variable gadget? No, because if I come back, I'll come back to a vertex I already visited, right? So I'll make that a different color. So if I go this direction, and then I continue here, then I'm going to take this edge, and I can't go back. I'm going to take this edge, I can't go back. I could take the edge going out to CM if I wanted to. There's no restriction there. But we're restricting it in such a way that we're not going to be able to come back on this edge, going back, the back edge to the variable gadget, because I'm going back to a vertex I already saw, which is not allowed in a HAMPATH. But if instead I'm going the other way, then I can go to CM and back. Do I have to go to CM in this variable gadget? No. I could, for example, in the XJ variable gadget go there. Or I could go in the XK variable gadget, I can go there. If I don't go to CM in any of the XI, XJ, or XK variable gadgets, will I ever visit that vertex, CM? No. By construction, we'll never visit that vertex, meaning this clause is not true because none of them had it go to CM, meaning the formula is not true, but I don't have a HAMPATH either. So therefore, this works. What if instead we had the opposite effect? So we had, let's say, xj bar, and we looked at xi or xj bar or xk, for example. And let's call this C, so many subscripts, S. So it's the S clause. Let's make another clause, a variable gadget. Let's see, there and there. And let's say that CS is over here. Then I have to, again, pick two vertices out. Let's say I pick these two. Again, it will matter which ones I pick, but I'm just showing you the main idea now. Should I do it in the same way I did it for the CM gadget above, like how I connected it, or should I do it the other way? Meaning that the right vertex goes to CM and the other one comes back. It's the other way, because we want to represent going left as the negative appearance of that variable, which is xj, and so this is xj's variable gadget, but I want to represent left as the negative occurrence, which it is in this clause. So I'm going to connect it up to CS this way. So it's the opposite order of the positive version for the XI gadget that we made before. Okay, so the XJ, whenever we have the negative version, we're going to go the other way. Okay? Any questions so far? So this is the main idea. There are some details we need to work out, but that's the main idea. So let's see. So among all possible HAMPATHs, just of the variable gadgets, yeah, go ahead.
Shouldn't you go to the CS from the leftmost of the two?
No, because xj is in the negative version in this clause. So in the positive version of the clause gadget, I want to have it be one of the ways. And then in the negative version, I want it the other way. So I just arbitrarily chosen going right as the positive version and left as the negative version. I could have easily chosen the other way. Yeah.
In this example, wouldn't you hit that second vertex twice, no matter what you did?
What do you mean by second vertex?
The second vertex on the bottom line there.
So you mean this one right here?
Correct.
So that means you're correct. If I go this way going in the positive direction, then I would. But if I go the negative direction, so in some sense, I'm forcing the direction. If I want this variable right here to be the witness of the clause, the thing that's going to make this true, I'm forcing you to go in one particular direction. And another thing that's a problem a lot of the times with these variable gadgets is that you could have some possibility of going through both directions of the clause. Here we're okay because we can't visit a vertex that we've seen twice, and we can't leave any vertices out. So if we start going one direction, then I have to keep going all the way to the end Because if I don't and maybe go to some clause over here and then go to some other variable gadget, I'm going to leave out some vertices. Okay, so actually let's look at that. So let's say that we have something like this, and then we look at another variable gadget down here. Something like this. And then we have some clause gadgets over here, doesn't really matter. And let's say we connect up to here in one of them. And then, for example, and of course we're going to have to go this way, or maybe we can go the other way. I'm not saying it's this particular way. And then maybe since each variable can appear in multiple clauses, maybe this second one goes back up and visits the same clause and then comes back some way. So it is possible via this to go around this path. So if I travel across here and then go up to this clause, I could, if I wanted to, there's nothing in the graph that says you can't do this, to go down to the other variable gadget, right? That's totally okay. And maybe, for example, this one over here allows me to go to this clause gadget, and then we have some other way to return to the other one, right? That's possible. So let's actually trace that out. So maybe we can continue here, and then we go over here, and then we continue off from this vertex, and then I continue this way. So I could do that, but is that a Hamiltonian path? No, why not? I just skipped at least one vertex, right? In fact, I skipped many more, potentially, because if I come down here, if I pick this direction, then I'm going to definitely repeat some vertices, right? Because I came down to this variable gadget, and that's not allowed at all anyway. But a problem might arise. If I pick the two vertices in each part wrong, maybe I want to be clever, and I put where they come back in the same place. So maybe in this long line of vertices, then maybe this one goes out somewhere, and then it comes back from the same vertex. And then maybe this one goes out to some vertex, some other clause gadget, and this one comes back. Right? That's entirely possible. So maybe I can have some other convoluted way of going to that first clause gadget, then coming down to some other variable gadget, going through some vertices, and then coming back to this original variable gadget and continuing on, and then I still have a HAMPATH. There may be a way to do that. So we're going to make one additional change here. We're going to insist that since there are k clauses, I know basically how many vertices I should have. And what we're going to do is this. We're going to, if we have a choice of two vertices that goes out and comes back, we must have a buffer vertex in the middle. So I'm going to make it blue. So I'm going to have a buffer vertex that can't be used by any clause gadget at all. Its only job is to connect its adjacent two vertices. It'll never be connected anywhere else. And then the next two will be going to some clause. So maybe this one goes to some other clause gadget and comes back. Then we have another buffer vertex. And then two more, and then a buffer vertex, and then two more, buffer vertex, two more. Since there are k clauses, essentially I'll need around 3k vertices in the middle, because for each one of them, I'm going to need two vertices, and for this buffer vertex, I'm going to need one vertex. Okay? So you could say, well, these first two are going to be assigned some clause C1, and then the next pair is going to be assigned C2, and then C3, and then up to CK. So the entire purpose of these buffer these buffer vertices is to ensure that I have to come back to the other vertex in order to get a HAMPATH. So if I don't come back there, then I'll miss that buffer vertex, and then therefore I won't have a HAMPATH. Okay? So that's actually all we really need. So then all we ask at the end is there a HAMPATH at all? Meaning that there must be a HAMPATH from the start vertex to the end vertex, to the bottom vertex. Why must there be a HAMPATH from only from the start to the end? Could there be some other HAMPATH that starts with some other vertex? We'll look back at the original construction. This top vertex has nothing coming into it, right? And these are directed edges. So that means there's no way to ever enter x1 from anywhere else. I have to start with x1 no matter what. And similarly, there's no way there's no way to go into this start vertex, whatever the name of it is. And similarly, the bottom vertex has nothing ever leaving it because it's not ever involved in any clause gadgets. The only vertices involved with clause gadgets are these middle ones in each of the variable gadgets. Okay, so let's actually do an example because I know we're all dying to have one. So let's do this. So let's do x1 or x2 or x3 and not x1 or x2. Actually, let's make x2 not false in the first one, and then x2 true in the second one, and x3 false in the other one. So how many variable gadgets am I going to have here? 3, because there are 3 variables. You may say 6. So why did I say 3? Yeah, the direction of the edges helps with the going back and forth thing. So let's see. So there are 2 clauses. So around how many vertices in the middle am I going to need? 6. In fact, well, let's just buff it up to say 8 or 9 or something. To have, maybe we could insert some buffer vertices on the ends if we want to. There's no harm there. Do you have a question? Or I thought someone raised their hand. Okay, so we have the start vertex up here. So this is going to be the x1 gadget. So let's put, okay, this is going to be quite a few vertices. Let's put 8. I think that'll be enough. So it's a lot of edges. I didn't anticipate this, but let's see what happens. So then we'll come back down. And the great thing about Notability is I can copy and paste stuff. So let's paste this, superimposed, and then paste. Oh, that's nice. I know it's slightly going right, but whatever, we'll deal with it. So this is the x2 gadget, and then this is the x3 gadget. Okay. Actually, we'll be okay. So the way that we're going to assign the 2 vertices to be the ones that go to, say, clause 1 are the 2 on the ends right here for each of them. And then we have the buffer vertex. And then the next 2 are going to be for the actually, we could have went through. I thought there were 3 clauses, but in fact, there are only 2, so we're okay. And then we can assign any of the other 2 as long as we have a buffer in the middle. So let's say these 2. So we'll put a buffer, and then these 2. And we could have put another clause if we wanted to, but let's not complicate it too much. Okay, so remember we got to have how many clause gadgets? 2. Yeah, because there are 2 clauses. So the first one I'm going to call C1. Second one I'm going to call C2. So C1 is the vertex over here. C2 is going to be here. So here's what we're going to do. In the x1 variable gadget, the first two vertices are corresponding to x1. So is x1 in the first clause appearing in the positive or the negative form? The positive. So we could choose either of the two directions, but let's just stick with our original intent and have it, so I'm going to use this in a different color, have going right as being in the positive form. So it's going to C1, going back. For x2, is it in the positive or the negative form for C1? A negative form. So it's going to start from the right vertex and go back. And for x3, it's pretty clear that it's in the positive form. So it's just like C1, although it's going to complicate the diagram quite a bit. Actually, here's an old trick. If you label the vertices, you can put as many copies of that same vertex anywhere you want. So what I'm going to do is this. Like that. Even though they look like different vertices than these clause gadgets on the right, they are the actual same vertex. Just like if you have, like in a Turing machine diagram, a transition that goes to Q except over here and another one that goes to Q except over here, it means going to the same state. Same thing here. Okay, x3 is in the positive form, so that means I got to go from the left vertex out to C1 and then back to the other vertex. Any questions on that? Okay, and then for the second, so I'm going to do this in, what's a good color? Purple. I haven't used that one yet. For the second clause, is x1 in the positive or the negative form? The negative form. So I got to start from the right vertex. So I got to do the opposite of whatever I just did. So I got to start from the right vertex and then go back. Oh, you're absolutely right. Thank you. My bad. Thank you. So I got to, but I was right in the sense I need to start from the right vertex and then go back. X2 in the second clause is in the positive form, so I got to start from the left vertex, go out, come back. And then X3 is in the negative form, so I got to start from the right vertex and then go back. So I'm not even going to begin to look at the graph in terms of all the Hamiltonian paths that it may have. In fact, there may be many, but since there are so many paths, I'm not going to look at them. Instead, we'll just look at a satisfying assignment and see that there's a Hamiltonian path there, I hope. So hopefully this works. So what is a possible satisfying assignment for the formula? So if I set all of them true, I didn't anticipate that, but if I set all of them true, then the formula is true. So another way we can look at this is using that assignment, let's pick out a witness of each clause to make the clause true. So in the first clause, I could pick either x1 or x3 to be true, to be the witness of that clause. So any choice? Come on, you got to pick one. X1, perfect. So let's pick x1. So we're remembering x1 as the witness for this clause, but I could easily pick x3. But for the second clause, I only have one choice, which is x2. So when we go down to these variable gadgets, I got to remember, I got to, on x1, on the assignment for x1, I got to go out to the C1 clause gadget, and then when I go down to x2, I better go out to the C2 clause gadget. And then for x3, at that point, since I visited both clauses already, I can pick either path through that I want. So let's see. So actually, let's do this in green. So since x1 is true, I'm going to go down to the left and across to the right, right? Because that means that the variable is in the positive form. So I'm going to go down this way. But that means at this point, since it's I could go to C1 or not, but it seems wise in our choice that we want to actually go to C1. So I'm going to go out to C1, to C1. And then I'm going to come back there. And so I'm okay so far. So I'm going to continue on my journey here. And so we've actually visited all of the vertices in the first variable gadget. Notice for the C2 in the purple for the X1 variable gadget, I could visit C2 without repeating a vertex because we flipped it to be the opposite. But if, for example, X1 was positive in the second clause, then I could also visit C2 if I wanted to, but I actually can't in this case. Okay, so for X2, we said that one was true as well. So I'm going to go down the same road. Actually, let's make it interesting. Let's change X3 to be false, which I'm allowed to do because X3 can be anything here. But either way, we're in X2. I can't go along the way to C1 in X2 because X2 is going the wrong way because then I'll repeat a vertex. So I have to keep going. And then here, it seems wise, I need to go to C2 because if I just keep going past it, I'll never visit the C2 vertex because it's not connected anywhere else. So I'm going to go along to C2. I can't go back up to X1 because then I'll repeat a vertex. So I have to come back, going down here. Then I continue my journey. And then I visited all the vertices in the X2 gadget, so that's okay. And so, in fact, I can just cross out C1 and C2 because I've already handled those two vertices. We said X3 is false, so should I go down the left way and across, or what? I should go down right and across left, because that's what it means to be false. But in fact, in this case, I can go either way. So, but in this case, I'm going to go to the right and then over left. I can't see C2 because I've already seen it before. But it's the same vertex, so I labeled it the same. So since I already visited C2 from before, I can't revisit it because it's a Hamiltonian path. So in fact, therefore, then we can come down. And did I leave out any vertex along the way? No. So in fact, we found a Hamiltonian path from a satisfying assignment. So we don't have enough time to do this, but a good exercise is start with an unsatisfiable formula. There's no satisfying assignment for it. And then see if the graph that you make actually has a logical inconsistency. There's no way to go out to the clause gadgets without repeating a vertex we've already seen. But in fact, since this formula is satisfiable, then we can find a Hamiltonian path. But to show that this is truly correct, what if I found a Hamiltonian path in the resulting graph? Can I resurrect the satisfying assignment? Well, let's see. I have to start from the top vertex, no matter what. So any Hamiltonian path must start there. I must go down either of the two directions. And then, for that reason, I must go over in one of the two directions. Then, whichever of the two directions it is, set the variable accordingly, depending on which of the directions that you went. And then if you ever visited a clause gadget and then came back, then that means that the variable is either in the positive or the negative form in that clause. And then since that's the only one that visits that clause, it can never visit it again. That's the witness for the clause being true. So set the variable accordingly so that the resulting value is true, either false or true accordingly. And then once you go all the way down to the end and do this for all variables, you must have a satisfying assignment because of the way that the graph is constructed. But you can resurrect the actual assignment from the Hamiltonian path, which is pretty cool. Any questions on that? I know it was a lot of stuff, but the overarching idea is what's more important. Yeah.
Can the three-side formula ever like tell us that how many vertices does the Hamiltonian graph have?
Yes. So great question. So in fact, we're not done showing NP hardness, right? What else do we need to show? That takes polynomial time. So how many vertices did I actually use here? Well, how many clause gadgets do I have? Let's say there are k clauses in the original formula. There are k vertices because there's one vertex for each of the clauses. Great. So k vertices for the clause gadgets. And then now, of course, the more interesting thing is how many vertices did I use for the variable gadgets? Well, think about it for a second. I occupy 2 vertices in each of the variable gadgets for each clause, but if there and also one more for the buffer vertex. So in fact, in some sense, I have 3 vertices for each clause. So in some sense, I have roughly 3k vertices for the horizontal bit, right? So let's see. So 3k for roughly for the horizontal part, and then 2 more for the top and bottom of each variable gadget. So it doesn't really matter, but let's say plus 2. But then how many variables do I have if there are n variables? So I'll have n variable gadgets. So this thing times n vertices for variable gadgets. But I could have a gazillion edges in here. But I can't have too many because for any pair of vertices, I can have at most 2 edges there, either in the one direction or the other direction. So in fact, whatever the total number is at most that number squared number of edges. So in fact, well, let's see, that's k plus 3k plus 2 times n. Well, that's certainly a polynomial in the size of the formula, which gave us n variables and k clauses, right? So therefore, this number is a polynomial in n and k. And then therefore, the number of edges is also a polynomial in n and k. So in fact, this reduction takes polynomial time. And then therefore, we can say that HAMPATH is NP hard. Any questions on that? Yeah.
Square that.
Yeah, so if we call that so many terms, t, then there are at most t squared edges. But the exact number is not at all important here. All I'm just saying is that it's some polynomial, therefore we're all set. Yeah.
For a graph, what is like the size of the graph? Is it the number of edges plus
A good question. It's depending on the representation, but a usual one that you do is say the adjacency matrix or adjacency list, edge list. So of course there are many things you can do. Another way you can do it is just like in the very first lecture, if you remember way back, where we listed all vertices, then a separator, then we listed all edges. But it's some polynomial, and then maybe some constant there, but it's still a polynomial. Yeah.
Doesn't this also show that HAMPATH is NP complete?
Yes, because we showed it was an NP earlier. So in fact, because of the result earlier, we showed that because of this, HAMPATH is NP complete. So quick question right before the break. What if I just made this graph undirected? So if I, instead of having direction on the edges, I just make the edge undirected. Does this still work? No, because now I'm not forced to go a particular direction, right? So for the ones that go to the clause gadget, one that goes out, one that comes back, I can go either of the 2 ways, right? Because they're undirected edges. So what about undirected HAMPATH? And we'll show that right after the break. So let's take a break.